So to continue where we left off last time, we were doing a bunch of array exercises and witnessing the pitfalls of not using pointers correctly, not using arrays correctly. But what I want to do now is these two exercises for the rest of the day here, and it's going to involve a little bit of background here. So one is we're going to write a function that creates a copy of a given array. Right? So what we could do is we could do something like I've got set up right here. What I've done is I've created an array of size 5, right? And here is 5. And then I fill it up with values 10, 20, 30, 40, 50, right? And then what I do is I create another pointer, b here, and I make it equal to a. Right? Now this is what's known as a shallow copy, because both of these references, both of these pointers, are pointing to the same thing. So when I do something like this, I set a equal to 42. Right? That will end up having a consequence and effect on b. If I print out the first element of b here, it's going to end up being 42. Right? Oops, clear. And then run it again here. Let's see. Okay. I never ran it again, I guess. There we go. There we go. So even though I never touched b, I never changed b, because I changed what a was pointing to, right? I changed a, but b was pointing to the same thing, it got changed as well. I've got that set up over here in Python Tutor to show you visually what I'm talking about. So I'm just going to go ahead and fast forward through this. Remember that a has been allocated, and then it sets its values 10, 20, 30, 40, 50. Okay? Now, a shallow copy here is going to make this pointer point to the same thing, right? So changes to one will affect the other. Changes to one will be seen by the other, right? So when I change 42, both A and B, they're referring to the same place in memory. Therefore, their first element is both changed to 42. This is what's known as a shallow copy. So a shallow copy is just simply a shallow copy is when two references point to the same memory address or element, right? Changes to one affect the other, all right? Affect the other. There we go. That's generally not what we want. Generally, when we mean copy, we mean a deep copy. Right? Two completely separate arrays or elements or whatever we're doing that contain the same values. Right? For deep copies, changes to one do not, emphasize not, affect the other. So how do we go about doing that? Well, let's go back to our CS50 IDE here and write some code that will make a deep copy. Right? So we're not going to do this shallow copy here. What I want to do is I want to make a completely new copy. We want to make a deep copy. Right? How are we going to do that? Well, we need a completely new memory space. A is up here. We need to copy it down to a different memory space. And for that, I am going to have to create that memory. Right? So I'm going to make another call to malloc, size of int, the number of bytes that an integer takes, times n, because you want to store n integers in there. And then, is that enough? Is it enough to create that memory space? Right. What's in the memory space of B right now? Well, let's test it. Let's visualize it. So let's edit this code, and we'll change it to this code so far. Right? Now when I run through this and initialize A to 1, 2, 3, 4, or 10, 20, 30, 40, 50, but then I make a deep copy, right? That is completely separate. These two things are completely different. But have I actually copied over all the values to this second array here? No. So that's our next step. Let's write the code to do that. What am I going to do? Just iterate over each element, right? And copy into B, the ith element of B is going to be the ith element of A. There. Right. Now let's visualize that. Edit this. and put that in there. Line it up so that it looks nice. There. Now, speed through this, 10, 20, 30, 40, 50, right? We create our memory space here so that it's completely separate, and then we iterate through each element in the original array and copy it over, 10, 20, 30, 40, 50. Now predict, will changes to 1 affect the other? If I change a sub 0 to 42, right, and then print out, printf, b sub 0 is equal to %b end the line, b sub 0. Will it be 42 or 10? It's still 10, right? I change one, but that does not affect the other because they're two separate, completely different copies. Again, looking at this in the visualization tool, right? Edit this code. Let's add that one chunk of code. And once again, I will, let me go ahead and jump to the last here, and then, there we go. All right, we're right about to the end, right? And then there. Did you see that change? 10 to 42, right? It's only affected in A because they're pointing to some completely different memory locations, right? So when we say deep copy, this is what we mean. Generally, when somebody says copy, that's what they mean, a deep copy, so that you're not messing with the original data. Okay? All right. Well, let's finish this up by, wow, that looks like such a useful function. Maybe there's already a function to do it, and there's kind of a function to do it. It's called memcpy. What do you think that stands for? Memory copy, right? Now, you can learn how to use it if you want to on your own, but let's go ahead and get some more practice here by writing a deep copy integer function. Right? So I want to, this function, doc style comments here, creates a deep copy of the given integer array and returns a new array containing its elements, ... Help me out. Help me write the prototype for this function first of all. All right, what should I call it? Should I call it just copy? What am I copying? First of all, again, you're polluting the namespace. You can only ever have one function named copy. Right? Copy int. Okay, that's a little bit better. Int array. Right? Or maybe just array, because if I say that it's an integer array, great. If I say that it's a double array, great. Right? That's part of the parameters. It doesn't have to be part of the name. Copy array. What kind of copy is it? It's a deep copy. Okay? Now, what are its inputs going to be? We're going to take a integer array. How do we represent an integer array? Is it just int array? Is it just one integer? Nope, it's many. So it is a pointer. Okay? Do we need to give it anything else? Is there any way for you to determine the size of an array? Down here, we're going to copy this code. I know how big it is because I put it into that variable. Up here, this integer array inside this function, is there any way to determine how big this array is? No. So what do we need to do? We need to pass in the size of the array. Usually, n indicates the size of an array, or m, or something like that. If you want to go with size of ARR, that's fine too. If you want to go with size, fine. Right? Generally, it's n though. Right? So it creates a deep copy of the given integer array of size n. If you want to put that in your documentation, that's even better, because you're saying what n is. And returns a new array given its elements. So is that going to be a void? Nope. Is it going to be an integer? One of them? No. It is a int star. By the way, if you want to, you can get rid of white space. That's ugly. Right? This is generally how I do it. Some people do it like this. Some people do it like this instead. Right? So let's go ahead and do it like this. Right? Just be consistent about it. Right? Why do I do it like this? Because that's how you do it on parameter variables, right? And I like to be consistent with those two things. All right, so deep copy array. Basically, all I need to do is copy this chunk of code here, right? That creates B, which is a copy of it, right? So copy, call it what it is, copy. And I called the array ARR of size n, great, return, copy. There. Now, the advantage of writing this as a function means that I can reuse this function all over the place. Deep copy of A, and it's of size n. Right. You want another copy of another function of another array? Great, you've got it in that function right there. The drawback to this, of course, is that what if you want a deep copy of the array for doubles? You're going to have to cut, paste. What if you want a deep copy of strings? You're going to have to cut, paste. And that's why C has that thing that I just mentioned, memcpy. Right? It is a catch-all function that will just simply take a chunk of memory and copy that entire chunk of memory over. If you want to, go ahead and read all about it and use it if you want to. Right? Okay, good. And let's see. All right, let's keep it going. What is my second exercise for the day? Write a function that takes an integer array and returns a new array, so kind of a copy, but only containing positive values in that array. So for example, if we created an array down here, and that's what I'll do with A now, int ARR, and I'll initialize this to just several values here, 5, -1, 3, 6, -7, 10, -1. That's good enough. How big is that? 1, 2, 3, 7. Int n is equal to 7. What I want, we want positives to be 5, 3, 6, 10, and that's it. Okay? So I want a function to do that for me. This operation in data science, if you want to call it, or if just data processing, is called filtering. I'm given a whole bunch of data, all 7 of these things, and I want to filter it out. I want to get rid of all the negative values. I only want the positive values. What about 0? 0 is neither negative nor positive, so I don't know, maybe we'll just say, no, we just want positives. Right? Let's start writing that function. Whenever I write functions, I always write the documentation first, because I want to put it straight in my head of what I want. Right? In fact, examples can go into documentation. So, creates and returns a new array of the given array of integers of size n, and with only the positive values included in the resulting array. Right? For example, if you called this function on this array right here, we'll go ahead and put this into the documentation. Oops, there we go. Then it would return this thing right here. And in fact, to be explicit about it, let me go ahead and add in 0 there to indicate that it would not include zeros. It only gives you the positives. Right? What would you call this function? Well, it's a filter function, right? And you can write a general filter function. We won't be doing that. We'll just keep it specific for now. Filter negatives, but you're also filtering zeros, right? So get positives, right? Positives only. Is that a good function name? I'll ask that. Functions are doing things. Functions are verbs. Positives only, that's a clause. I don't know what that is, right? So we want it to be get positives. Positives. Right? There we go. Okay. Help me write this function now. It needs to take an array, right? So it needs an integer array and its size. But that's got me thinking, would I be able to make changes to that array? Arrays of 0 is equal to 42. Yeah. Remember last time we demonstrated that if you're just going to sum something up, should you be able to change that? No. How did we make that promise that we weren't going to change your data. We were just going to make a copy of it for you. Here you go. By placing the const keyword in front of it. In fact, I'm going to go back and make sure that promise is everywhere. That deep copy array, I'm going to make a promise. I'm not going to mess with your data. Right? I am going to copy your data and give you a brand new deep copy of it. Read it, but reading it is the only thing I'm going to do. I'm not going to write to it. Likewise, I am not going to screw up with your original array here. I'm going to create a new array of some new size and then return that to you. So the return type is here is int star as well. Okay. Good so far. Okay. Well, I know how big the original array is. Do I know how big the new array is? For this particular example I do, right? Up here, there were 8 elements, but in the result, there's only going to be 4. So if I'm going to create a new array, int result, how big do I make it? Int star malloc. Do you know that it's always going to be 4? No. Well, how did I know that it was going to be 4 here? Well, okay, there's 1 positive. That's not it. That's not positive. There's 2 positives. Right? 0 is not positive, so we skip that. 3. Negative 7 is not positive, so 10. Oh, 4. And then we get to the end. Right? That was pretty easy. All I needed to do is go through it once and count up the number of positives. Right? So let's do that first. Right? Count up the number of positives. 4, int I equals 0, I is less than n, I plus plus. At this point, you have probably written the same for loop over and over and over again, and now it's muscle memory. You're just going to start typing this out. This is why it's an idiomatic for loop. Right? That is just something that you'll get used to typing over and over and over again. So for each element, if the element is positive, greater than 0, then I will increment a counter. Right? That means I need to create that variable, int counter. Is that correct? On line 63. As of line 63, what is the value stored in counter? Again, who knows? There is no default value defined by the C standard. So if it were, some random value like 42, right? Are there 42 positives in that example? No. What should I initialize this to ensure that I'm counting correctly? 0. There's the number of positives. At that point, I can just say size of int times counter. There. And then eventually return that result. Does that get me what I want, though? Get positives. Let's come down here. And let's put in that 0 just to make sure that that test case is correct. We want positives. So int pos is equal to get positives of array n. And then 4, int I equals 0. I is less than something. I'm not sure. I plus plus. Printf pos of %d is equal to %d. And by the way, I've written the same for loop over and over and over again just to print out an array. What would have been a better idea? Write a function to do it. Right? Okay, so, but this is good enough here. And then I and pos I. Except that, do I know how big that array is? I know how big it is because of this example. It should be 4. So let's just hard code that for now. I know how big it should be. Yeah. Oh, duh. There we go. I can't just it away. There. 0, 0, 0, 0. Is that correct? Obviously not. I want 5, 3, 6, and 10. Simply just creating memory doesn't copy anything, as we already saw with deep copy versus shallow copy. All right. So what do I need to do now? Now iterate through the original array and copy over values, but only if they are positive. ... Okay. 4, int I equals 0, I is less than n, I plus plus. Right? Again, that idiomatic for loop. If it's positive, then copy it over, dot, dot, dot. So this is a direct copy of this up here, right? That's how you have to do it, unless you're going to do something more clever. There's really no, I mean, you have to go through it once in order to count up the number of integers that are there that you need to allocate memory for. There's really no way around it. You can't predict how many things are going to be positive. You could, of course, maybe take this chunk of code right here and put it into another function. That function would then report back to you that there were so many positive values in there. Right? And that would simplify this function a little bit, but we'll save that for an update. All right, how do I copy it over, but only if it's positive? I want to copy it into the result, so of something is equal to array of I. Right? The ith value is being copied over into this result. All right? What is my index over here? Is it I? Now, think about this with the example. You would copy over 5, that would work. You end up not copying this over, but then you end up copying 3 at what index value? Index value 0, 1, and 2. Does that look like the index value 2? No. There's a gap here. Right? So help me think this through. Right? I'm going to be iterating on this one. That's my first finger here. But I'm also going to be iterating on the second array. That's another finger right here. So I'm going to iterate over each one of these elements and copying it over down here. Once I make a copy, like say 5 is copied to 5, then I move this one over and I move this one over. If I don't copy it, I move this one over, but I don't move this one. Right? 2 fingers suggests how many indices? I and probably a different one, J. Okay. Where does that J come from now? Got to start somewhere. So what should I start J at? Where do all arrays start at? 0. Okay. After I've copied something over, I need to set myself up for the next iteration. What should I do with J? This is I up here, and this is J. I'm copying from this one down to here. So I to J. What do I need to do now? J plus plus. There we go. Compile this, see if it works. 5, 3, 6, 10. Was that correct? 5, 3, 6, 10. Looks like it to me. 5, 3, 6, 10. Right? All right, now let's come back over here and let's change this. Let's add another one. 9. I don't know. 10. I already got a 10. 42. There we go. So now what should it be? 6 elements should be copied over. And should still work. It doesn't. 5, 3, 6, 9, 42. I added 1, 2, 3, 4, 5, 6. That should be 6, right? What am I missing? 5, 3, 6, 9, 42, 10. Oh, thank you. There, I do need to change n. How many is there? 1, 2, I added 2, so it's just 9? 4, 4, oh no, there are 10. There we go. I added 3, I guess. There we go. All right. So, yeah, I do need to keep track of that. I'm expecting 6 now. All right, well, I'll go back over here and change 42 to negative 42. Is it going to be 6 anymore? Nope. 5. All right. No more hard coding of that thing. Let's solve this problem. All right. How do I know how big that resulting array is? So when I told this function, here's the array, and here's how big it is, right? I knew both of those things, and I gave it to the function. The function is going to give me an array, but it also needs to tell me how big it is. it would be really nice if I could return two things, right? That doesn't work like that. That's not a function. Right? So we also need to communicate back to the calling function, how big the resulting array is. Right? We can't return two things, except that I seem to remember when we introduced pointers, I said that one of the use cases was you can return two things, right? You can return. I forget what the example that we did was. What was it? That you can return two variables or three variables. Does anybody remember it? I don't remember it either. But I do remember the example in the pre-prepared videos. If you want to do compute both the circumference and the area of a circle, right? You wanted to compute both of those things at once. How did we end up doing it? Int or void, say, right? Some function. Right? If I want to return two, here's my input. Right? I want to return two things. I do it through pass by reference variables, A and B. Right? In fact, this is what you've done this week. Right? It's not A and B. Well, let's look at the example from this week. Right? So you want to convert RGB to sepia toned or something like that. To sepia. There we go. Int R, int B, RG, int RGB. There we go. Right? Three pass-by reference variables. Right? That's a way that you can return three values all at once. Right? So our solution here is to introduce yet another variable. Int size of result. I'm just calling it that because that's what it is for now. Now, is that a pass-by reference variable? Nope, that's a pass-by value. Can I return that? No, it's only input. Right? So let's change this to a pointer. Now, what do I do with that pointer? Once I know how big the size is, counter, I can set that variable to size of result is equal to counter. Is that correct, though? The thing on the left-hand side is a pointer. The thing on the right-hand side is a regular old variable. How do I resolve these two things? How did you resolve it with RGB? How did you set the red value? Star in front of it, right? Star, red, you set that to, I don't know, 123. Right? This is wrong because R would be a pointer, and setting it to the memory address 123 doesn't make any sense. Right? Let's come down here. Int M. There we go. Oops, I need it up here. There we go. Now I'm going to pass that third value, M. And now I do know how big that resulting area or array is. Except that, what do I need in front of my M? Let's ask the compiler. Right? Warning, it makes a pointer from an integer without a cast. Right? This is just a regular old integer, but it expects an int star. So how do I take a regular old integer, regular old variable, and convert it into a pointer? Ampersand. There we go. And there. Now it'll compile. Now it'll work for this one. It'll work for this one. 42 should now be in there. It'll work for anything. I could mash my keyboard here. There we go. And as long as, how big is that now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17. There we go. 17. There. I'm getting them all. Right? Looks like it to me. So this function here represents pretty much everything we've done in this course up to this point. We've got pointers. We've got passing by reference. We've got arrays. We've got dynamic memory allocation. We've got loops and conditionals. Basically, this one function has an example of everything that we've done. Right? Nice. I'm going to put that into the notes over here with this exercise. All right. Okay. Using various functions. Okay. Any questions? No? All right, then, let's talk about multidimensional arrays. So there's normal data. What if I had data that looked like this? 1, 2, 3, 4, 5, 7, 6, 5, 4, 3, 8, 7, 6, 5. There we go. All right. So we've got one row of data, a second row of data, a third row of data. Vertically, what are, I think I can do this. Let's try this. Nope. What is it? Nope. Nope. Darn it. There we go. There. That vertical selection right there, what would you call that thing right there? So for if each one of those lines is called a row, what is this thing? Column. Good. By the way, if you want to know about vertical selection, or it's actually called block selection, I just learned the quick key. No, that's not it. I just lost the quick keys. There we go. Pretty much any IDE will support this. That you can have normal selection mode, right? It's just, selecting. You can go ahead and hold down the shift key and click somewhere else, and you'll get a line selection. If you hold down on the Mac now, if you hold down Option and Shift, you have what's called block selection mode. You can go ahead and select a block of code like this. Right? It's kind of wonky on the CS50 IDE, but most IDEs will support something like this. So that if you want to select, say, just one column of data and then copy it over somewhere else, you can. Copy and paste. Pretty cool trick, right? Kind of turns your text editor into an Excel file where you can select rows or columns or whatever, right? And again, on Mac, that was Shift Option to do block selection mode. Okay. Anybody have their Windows machine open? Does it work? What's the Option button on a Windows machine? Control? Is it Control Shift? It's not Control. Alt, probably. Alt Shift. So Alt Shift at the same time, and then you can select it. That works? Okay, Alt Shift. There we go. So now everybody can play along, right? Anyway, what do you call this entire thing? So we've got rows and we've got columns. We call that one row would probably be a list. Okay, mathematically, it is a matrix. Just normal data-wise, it's just a table, right? So how do we do table and matrices, tables or matrices in C? These are called multi-dimensional arrays. Right? So a regular old array is a 1D array, one-dimensional. Right? You can have 2D arrays, 3D with rows and columns. Right? These are also called tables and matrices, right? Or matrix. A matrix is one, matrices is the pluralization. And by the way, yes, you can have 3D, 4D, etc., but don't, right? If you have need for three-dimensional data, four-dimensional data, there's probably a better solution. That better solution is going to be what's called a structure, which we'll talk about much later. But 2D arrays make complete sense. 2D arrays are tables. 2D arrays are matrices. Right? 2D arrays are palettes of pixels. Right? That's something you're going to do next week. An image is nothing more than a table of pixel values. Right? So you'll be able to manipulate this image in your lab and hack using matrices and 2D arrays. Right? So in C, a regular old array of integers is a pointer, int star array. Right? A 2D array is two pointers. Right? So int star star array. Now before we get into it, that looks familiar. Star star. Where have we used that before? Int argc char star star argv. So what do you think argv actually is? It's a table of individual characters. The first row is the first argument. The second row is the second argument. The third row is the third argument. But instead of numbers, they end up being letters. Hello. Right. Goodbye. Right. Right. And so now we're starting to understand what that star star was. Right. Okay. Well, if that's how that works, then how do we use it? Right. Once you have a 2D array, you specify the row and the column index. Right. For example, if I go, what did I call it, matrix? Oh, yeah, I should have called it matrix. I'm not going to call it array. I'll call it mat or tab for tab. No, let's just call it table because that's what it is. Table sub 0, 0, or say 0, right, is the 0 row, first row, and 0 column. That is first column. If there are n rows and m columns, the very last element, that is last row, last column, is at, help me. So if this were a normal array, 1D array, where would you say the last element is? N minus 1, because we start counting at 0. If this is the last column, and it's m minus 1. Right? So you always provide two indices. The first one is the row. The first index is the row. The second is the column. This is known as row major form. Right? You can talk about column major form, but that's weird. Only really weird linear algebraists would do that. Even the normal linear algebraists would still go with row major form. All right? All right, good. So how do we allocate it? How do we allocate memory for a 2D array? Right. Well, we need to do it in phases. You do it in phases. Right. I don't have a visualization. We'll go ahead and use this as the visualization. So let's edit this code here. Let's just do it in here. Okay. So my matrix or my table is going to look again like this. Let me initialize this to null. Okay. What I need to do is I need to set up each row. I need to set up the first row, which is just a regular old array. Then I need to set up the second row, which is just a regular old array, third row, fourth row, fifth row, etc. Before I do that, I need a way to keep track of each one of those rows. So let me go ahead and initialize a double pointer. This is sometimes called a double pointer, right? Because it's a 2D array. So let's go ahead and call malloc, right? And I want a pointer to a pointer, right? This is a pointer to a pointer. Malloc, how many of them do you want? Well, let's establish that first. I want, I don't know, 3 rows and 5 columns. Rows. There we go. All right. So how many bytes is that? Well, let's take care of one thing at a time. How many rows do you want? I want 3 rows, right? Or n rows. How many bytes does each pointer to a row take? Size of int star. Because a row is not a star, or a row is not an integer, excuse me. What is a row? A row is a regular old integer array. And how do we represent that in C? As a pointer. Excellent. Right? No, sorry. I needed a star. I'm getting ahead of myself. This should be down here. Right? There we go. So this is a pointer to a pointer. Yes, this is correct. Right? Now, initialize each. Forget about the spelling. Each row. We've only got 10 minutes. Don't have time for correct spelling each row. We never take off for spelling, by the way, in any of your labs or hacks, unless, of course, the misspelling leads to a compiler error that doesn't get anything to work. But if you ever had any comments in there that were misspelled, we'll note it, but we're never going to take off for it. Right? It ain't an English class. Right? So for each row, I equals 0, I is less than n, I plus plus. Create the ith row, which should have m integers, dot, dot, dot. Well, we all know how to do that because that's just a regular old array. Right? So table sub I is equal to int star, call to malloc, and everything here is just normal. How many do you want? M of them. How many bytes does each one take? Size of int. Right? Now, I was correct. Darn it. I'm 99% positive that this is correct, I think. We'll find out when we visualize it, and if it doesn't work, then we'll come back on Monday and fix it. Right? So each row is a regular old integer array. Oops, not saving the web page. All right, there we go. Let's visualize this and see if it comes out. Okay, so I've got 3 rows, 5 columns each. I have a table pointer that's pointing to null. We're initially going to point to this array of pointers because each one of these is going to point to a row, to a row, to a row. Watch. For the first one, this pointer will now point to the first row of 5 elements. On the next iteration, we'll make that second pointer point to the second row. On the third iteration, we'll make that third pointer point to the third row. Now this one is not our actual data here. This is just setting up the data. Here's our table of data. How many rows does it have? 3. How many columns does each row have? 5. Right. Let's edit this code and muck with it. Right. So initialize each value to some other value. Dot, dot, dot. Right. For int I equals 0, I is less than n, I plus plus. Now that same pattern of an idiomatic for loop can be applied to each row. Right? This only goes for the first row, second row, third row. For each row, now I need to iterate over each element in that row. That means another for loop. I can't use I, so I'll use j. J is less than n, j plus plus. Right? And table sub something something is equal to, I don't know, I plus j plus 2 or 3. That's good. Right? How do I access each individual element? I and j. Now again, let's visualize this execution. We set up our memory. Row 1, row 2, row 3. Now as I go through this for loop, it's going to go along the first row, each column setting them equal to values, 3, 4, 5. Oops. Did I screw? Oh, I did screw up. It's not NN. What is it? NM. There we go. There, and jump ahead, jump ahead, jump ahead. There we go. All right. So now it's going to go through the first row, 3, 4, 5, 6, 7. And then that inner for loop will be done executing. It'll jump out to the outer for loop. I will now be incremented to 1, meaning that we're going to work on the second row right here. Next, 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 next. Right? And then I gets incremented to 2, and we're working on the last row here. Excellent. Right. Okay. One last thing in the last 5 minutes here. Let's clean up after ourselves. Clean up. Right. I need to free this memory. Can I just free the table? So I'm going to jump to the end and then go back because there are too many steps. Last. There we go. All right. So we've created our data. We've processed our data. We're going to do whatever we're going to do with our data. I'm about to free up the table. What is actually going to be freed up when I free table? This is the table right here. Just these 3 pointers. What about all this data down here? Nope. it ends up being lost. Right? Again, let's go back here. Right? Just freeing up this one thing right here, this thing right here, is not going to clean up all of this memory down here. So when I have a 2D array and I've set up an initial array of pointers and then row, 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 I need to work backwards. I need to clean up each row first. Right? For int I equals 0, I is less than n, I plus plus. And I free the ith row. Only after I'm done with all that can I free the table of pointers. Right, visualize this. And again, let me just jump to the very end and then work backwards here. There we go. All right, so there we are. I'm going to free the first row. You can work backwards literally if you want to. It doesn't matter if you go top to bottom or bottom to top. I need to free up the first row. There. That point, the def thing here means a pointer to a memory is either unallocated or misaligned with data boundaries because we freed it up. Right? It's dead memory now. It's not just question mark memory. It is do not touch this memory because it's undefined behavior. You freed it up. Now we're about to kill the second row. There we go. Then we're about to kill the third row. There we go. All right. Now after we're done with all that, can we kill the table? All right. So if you create memory, often you have to work backwards. Okay? All right. Excellent. We'll pick it up there on Monday. I'll make sure you got this in the notes, though.